Hello everybody, and welcome to example 5 on page 70. This is going to be an example demonstrating how we can use the previous theorem that we talked about to come up with a formula for a linear transformation. Okay, so let's read this together. By completing the following outline, find a formula for the linear operator t on R2 that reflects every point in the plane about the line y equals 1/2 x. Okay, so to help us visualize this transformation, we have a picture over here to the right. Notice that this line is y equals 1/2 x. It has a slope of 1/2 that goes through the origin. And before we dive into the question itself, let's think about what this linear operator is doing. So it's essentially taking a vector v, I'm just going to take that as an example, and reflecting it straight through the line 1/2 x. So to figure out what the output of v is, you would just kind of draw a line perpendicular to 1/2 x and then keep going so that you come out an equal distance on the opposite side. So t of v would be the vector that's there. And what we want is a formula so that if somebody hands you a vector like v, gives you specific coordinates, you can plug that into your formula and out is going to pop the output, okay, for every point in the plane here. So that's where we're trying to go with this. All right, so let's clear away some of the clutter here. And part A gets us started on this process. It would like us to consider the ordered basis beta prime equals 2, 1 and negative 1, 2 for R2, and to use symmetry to calculate the matrix of our linear operator relative to this basis. Okay, you might be wondering, why would we choose such a strange basis? Well, I think once we get to the end of part A, you might see some motivation behind that. Okay, so how do we calculate this matrix? Well, it's about taking our two vectors and substituting into our transformation. Okay, so we're interested in determining what t of 2, 1 is and what t of negative 1, 2 is. Okay, so we'll leave that blank for the time being. And then once we have an output, we would like to write that output, whatever it is, as a linear combination of the same basis vectors, 2, 1 and negative 1, 2. Okay, well, before we can do that, we need to know what actually happens when we substitute those two vectors into our transformation. And let's start with the second of the two. I think that might be easier to start there. So where is the vector negative 1, 2? Well, in our picture, that would be sitting up here. I'll draw it as an arrow. And to get t of negative 1, 2, we want to take that vector that we just drew and reflect it straight through the line 1/2 x. The nice thing about that vector, negative 1, 2, is that it happens to be perpendicular to our line. And so t of negative 1, 2 is going to come out exactly opposite to it, like that. So t of negative 1, 2, then we can see from the picture, is going to be 1, negative 2. Okay, and now the question is, how do we fill in the blanks to make that a true statement? Well, notice that 1, negative 2 is the reverse of this vector, so we can get it by putting a negative 1 here and a 0 there. Okay, second thing we want to do then is to figure out what is t of 2, 1. Okay, well, where is 2, 1 in our picture? That's this vector right here. And what would happen if you took that vector and reflected it through the line y equals 1/2 x? Well, it's right on the line y equals 1/2 x, so when you reflect it, it's not going to move. Okay, it can't come out the other side because it's already on the line, and so what that means is that we're going to get the same vector back that we started with, 2, 1. Okay, and notice that we can get that vector if we fill in the blanks with a 1 here and a 0 here. Okay, so kind of back to that question then of why would we choose this basis? Well, it's because the symmetry made it very easy to figure out what the numbers are that go in the blank. It's a convenient basis for this particular transformation. Okay, and so we are ready to write down the matrix of this linear operator relative to beta prime. Okay, so the first column is going to be these two numbers, 1 and 0. Okay, and the second column is going to be these two numbers, 0 and -1. Okay, nice simple matrix, again, because we chose our beta prime in an appropriate way. Okay, continuing on here then, let's see what part B is asking us. So now, let beta denote the standard ordered basis for R2. Calculate the change of basis matrix Q for taking beta prime coordinates to beta coordinates. Okay, so to do that, we need to start by writing down the beta prime vectors. And then just asking, how would we write those as a linear combination of the beta vectors? Well, beta is the standard basis, so that's kind of an easy question. 2 times 0, 1. Okay, and that implies that our change of coordinate matrix is just going to have 2 and 1 in the first column. Okay, and then -1 and 2 in the second column. Okay, and there's our answer to B. All right, and now here comes Theorem 2.23. Okay, so they'd like us to, and that's the theorem that we looked at in the last video, use Theorem 2.23 and the fact that the inverse of a 2 by 2 matrix is given by this formula to calculate the matrix of T relative to beta. Okay, maybe if you've taken a course involving matrices, you might have run across this formula before. We're just going to accept it and use it in the problem that we're doing here. Okay, so we have, okay, I'm going to try to be careful and not run out of space here. Okay, so one of the two formulas that they gave us in Theorem 2.23 said the following, that the matrix of T relative to beta is Q times the matrix of T relative to beta prime times Q inverse. Okay, we've done all of those calculations above, so just filling those in, let's see, Q was 2, -1, 1, 2. The matrix of T relative to beta prime, you can look up at part A and see that that was 1, 0, 0, -1. Okay, and then Q inverse, we're going to use this formula to calculate it. So we're going to get 1 over AD minus BC. So let's see, what would that be? A times D minus B times C. You can double check and notice that that's 5. Okay, 2 times 2 minus -1 times 1. Okay, and then D negative B negative C A. Okay, if we fill those in, we're going to get 2, 1, -1, 2. I'm kind of leaving it up to you just to look at that formula and make sure that I wrote down everything correctly there. All right, now we're going to do the multiplication here. So if we multiply those first two matrices times each other, we are going to get, let's see, 2, 1, and 1, -2. Okay, there's that 1/5 again. 2, 1, -1, 2. Okay, and what I'm going to do just to make this a little easier is to take this 1/5, that's a scalar, and move it to the front. And then multiply the two matrices that are left over by each other. So this times this. If you multiply those 2 by 2 matrices together, here's what you should get. 3, 4, 4, -3. And you know, actually, just to save a little space here, I'm thinking it might be a little tight. Let's move that up to the line above it. So we're going to get 1/5 times 3, 4, 4, -3. Okay, so there's the matrix of T relative to the standard basis. Okay, now, here comes kind of the main step. Find a formula for T. The fact that this matrix that we just came up with is relative to the standard basis makes it easier to write down a formula. Okay, and so here's my claim. Therefore, since beta is the standard ordered basis, our formula is T of xy equals 1/5 times 3x plus 4y. Notice that the 3 and the 4 just came from here and here. And then the second coordinate would be 4x minus 3y. Okay, those numbers come from here and here. Okay, if you're wondering kind of how we made that leap, maybe think about it this way. If you were to take 1/5 times 3, 4, 4, negative 3 and multiply it by xy, okay, you would get 1/5 times 3x, I'm sorry, I'm running out of space here, 3x plus 4y and 4x minus 3y. That's really the same formula as what we wrote down here, just that we've written it in row form instead of column form. Okay, and so if we've done everything correctly, this is the formula that it was our goal to find at the very beginning of the problem. Okay, this should tell us how to reflect any point in the entire plane R2. Okay, just let's make ourselves feel a little bit better about this and see if we really believe that this formula is plausible that we came up with. So I'm going to call this a point check that we're about to do here. Okay, I'm just going to pick a point, okay, and go up to the picture here for a minute. So what if we pick the point 2, 3, let's say? Okay, I'm going to clear a little clutter away here. So 2, 3 would be right there. Okay, I'm just kind of picking that out of the air. Okay, let's plug that 2, 3 into our formula and see where it puts us. So t of 2, 3 would be, we're going to use the formula that we just derived here, 1/5. We're going to plug 2 in for 3 and, or 2 in for x and 3 in for y. So 3 times 2 plus 4 times 3, that would give us an 18. Okay, and the second coordinate, 4 times 2 minus 3 times 3, that's going to give us a negative 1. Okay, we can maybe simplify that a little bit, 18/5 and negative 1/5. I'm going to go ahead and write that in decimal form. That would be 3.6 and negative 0.2. Okay, so let's plot that point up above, 3.6 and negative 0.2. Okay, so that's, let's see, 1, 2, 3.6 is about here, and negative 0.2 is maybe about there. Okay, so 3.6, negative 0.2. And what do you think? Does that look like a plausible output? Notice that it kind of does, because if you take this point 2, 3 and reflect it straight through, that looks about right, okay, where that point ended up. Okay, so that lends a little bit of credibility to the formula that we came up with, and you could maybe try some other points and convince yourself that this formula that we came up with really works here.